So, welcome back to our lecture on projective geometry. This time I want to talk about join, meet and other constructions in the situation of the real projective plane, and for that we go back to our axioms for general projective planes. You remember our two axioms? We had A1, for every 2 points there is a line joining them, and for every 2 lines there is a point that is at the same time incident to them. We call this here the join, we call this here the meet, and what we're actually looking for in both cases is just for a vector that is simultaneously orthogonal to the two representants. So if we want to calculate the join of 2 points, and here I've written down only the representants, not the equivalence classes, you can easily check that everything is well defined and that it's okay to make the calculations on the representants. So what we are searching for is a vector that is at the same time orthogonal to P and orthogonal to Q, and we get that by the cross product. So the situation looks as follows. We have our 2 points here represented by 2 orange vectors, and the line incident to them corresponds to the vector at the same time orthogonal to both of them. And you also see this operation only makes sense if P and Q, the corresponding vectors, are not linearly dependent, because if they are linearly dependent, the line is no longer unique and the cross product here really vanishes. The situation is close to identical if we do the opposite question. If we ask for giving 2 lines L and M and asking for a point on both lines simultaneously, we will see, well, it also must be a vector that is orthogonal to both of them. So here again the lines are represented by blue vectors and the point is represented by an orange vector, and you see, well, essentially we're looking for one thing that is simultaneously orthogonal to both of them. And the main point about that picture here is that these two images here look almost identical. The only thing that is different from one picture to the other is the color of the vectors, but the calculations are identically the same. If we consider the whole thing in the embedded situation of the standard embedding, then we will see we get different interpretations of points or lines. But before we do that, let me show you one more picture here. Talking about collinearity of 3 lines means, well, we are looking for 3 vectors that are at the same time orthogonal to the same vector representing a line, which means that those vectors here must be linearly dependent, which can be checked by a determinant bearing 0. Let me show you this situation once more, but this time in the standard embedding. So, and there we will see that this exactly models collinearity in our usual space. So we have 3 points. From those 3 points we get 3 vectors by the standard embeddings. If we are looking for one line that is simultaneously collinear to all these 3 points, if they are collinear, then we are finding one vector that at the same time is orthogonal to each of them, and this vector now defines a plane that's orthogonal to them through our 3 vectors, which, if we cut it with our embedding plane, exactly corresponds to our line. So you see, everything translates nicely, but from a purely mathematical point of view, we could just deal with vectors. We don't have to think about points and lines, and we even don't know that the line at infinity plays a special role. This only comes from our interpretation with the standard embedding. Similarly, we can check, and I ask you to do the pictures for that yourself, that three lines meet in a point if the corresponding vectors are linearly dependent, which we can check again by a determinant being 0. One more important point here, if we see, say, three lines meet in a point, this could also mean that these three lines meet in a point at infinity, so a point that is very far out. So I want to do a few typical calculations in that setup, and now I again go back to the vector point of view. So a typical calculation would be, for instance, I give you two points A and B and ask you to form the line, and C and D, and again ask you to form the line and ask you to calculate the point of intersection here. After everything we said so far, this simply means that you have to calculate the join of A and B, which is nothing else but the cross product, and calculate the join of C and D, which again is nothing else as the cross product. Some other people call it the vector product. And then you have to calculate the join of these two things, which is again the cross product here. And there is a nice different way to do that calculation, which I've written down here, and I use the little shorthand because we will have to deal with determinants very, very often, and for that I from now on will use a shorthand that if we have 3 points x, y, z in homogeneous coordinates, then x, y, z forms a 3 by 3 matrix, and the determinant of this 3 by 3 matrix will be abbreviated by such a kind of bracket expression. And this point P now can be calculated as determinant ABC times D minus the determinant ABD times C. And you may ask why this is the case. So let me give a brief explanation of what's going on here. Though first of all, this point P, if it's calculated this way here, is in the span of C and D. So by definition, if we take a linear combination of C and D, we must get a point on the line CD. So if we do that calculation, P must lie on that line. Why does it also lie on A and B? And for that, simply insert this point here in a bracket with A and B and check if it is really 0. And if you do that calculation, then you get, well, you calculate A B times A B C times D minus A B D times C, which the determinant is multilinear, results in A B D times A B C minus A B C times A B D, which has no other chance as being 0. So you see, you can easily calculate this point P, not only via these vector products here, but also via this nice determinant calculation. So let's come back for a moment to the standard embedding and think a little bit about parallel lines. So what we should expect is that parallel lines meet at points that are infinitely far away. And let me just check by calculation that this is indeed the case. So assume we have two lines which are assumed to be parallel to each other, these two lines should be spanned by 2 points, and we are looking for the point of intersection of those two lines, which is considered to be very far out. So what do the calculations say? And now we think of everything in the standard embedding. So let's take A and B as 2 points on those lines, and let's define these two other points by shifting the points A and B into the same direction. Let me do that in concrete calculations in the standard embedding. So we have a point A and we have a point B in standard embedding, and we have a point R, or a shift vector R, that such that if we add Rx and Ry to our coordinates of A and B, we should get those shifted points. And to get these shifted points here, I really had to put a 0 in here. If I add A and R, I really get a vector that is shifted in the direction of R away from A, and still remains in the standard embedding because it has a 1 down here. And now let's do the calculations. So first of all, we can calculate the join of A and A plus R. So if we do that, so we have to take A plus R times A with vector product, and the vector product is linear, so A times A vanishes, and what's left is R times A. Similarly, the other line is B plus R times B, which is nothing else as R times B. Now we want to take the mean of those two lines here and calculate this, and if we do so, so we calculate this point P far out there, which now is the vector product of those things. And with our formula from the last slide, we learn that, well, this is essentially this expression. And if you look closely at this expression, you see that this term here vanishes because R happens to be twice in this determinant. So the only thing that is left is some factor times R, which means that our point P is essentially the same thing as our point R. It only differs by a scalar multiple. So the point at infinity that we get is actually our direction vector R. So one more thing in the standard embedding, and I always have to emphasize we are in the standard embedding now. So we singled out a certain line at infinity and a certain drawing plane. So the projective plane itself doesn't know the difference between the line at infinity and any other lines. But we can say, well, we are in the standard embedding and one certain line plays the role of the line at infinity, and by that we can, for instance, try to construct the parallel through a point P to a line L. And how to do so? Well, we need the line at infinity. So symbolically I've drawn it here into that calculation. We have to calculate the point that is very, very far out on L, which is this point capital L, which is L intersected with the line at infinity, and from there we can calculate the join to P and see that this is the way we have to calculate the parallel. Once more, I want to emphasize this makes only sense if we give a certain line, the line at infinity, the role of being a special line at infinity and defining parallel. So we define parallelity with respect to that line. that we say, well, all lines that meet in that line are called parallel. So here once more, a three-dimensional picture of what's going on. Again, I have my lines, and now I, in addition, joined the point of intersection with some other point here and start to move my lines. And you see, as soon as my vector moves far out, those lines here get a parallel position. Again, I try to hit this parallel position, and you see you have well, this point here, which corresponds to a vector being very far out, corresponding to a point at infinity, and these things are parallel because they meet at infinity. Let me end this lecture with a little bit more elaborate construction, and let's do it this time from a standard viewpoint, so from our usual Euclidean plane, and from a projective viewpoint. And the task I want to do is I take 4 points of, say, a square, and I want to calculate 2 lines that are in the middle of both sides. So how would I do it in usual terms of usual geometry, where I can deal with parallelism? So I would say, well, first of all, draw this diagonal, then draw this diagonal, and get this point of intersection, which is in the middle of the square, and then simply draw a parallel from that point to one of the sides and a parallel from that point to the other of the sides, and you will get 4 equal smaller squares in here. So projectively, we cannot do that right away because we do not have the operation of being a parallel. For having this operation, we somehow have to talk about points that are infinitely far away. So let me redo the same thing in a projective setup. Say I start again with my drawing, and then I said I want to calculate this point of intersection. This is still completely possible, but now when I want to draw, well, this parallel point here, line here, I first have to get the point at infinity and then join this point with this line, and then I have to do the same thing in the other direction. It looks very similar, but it is intrinsically another point of view, and by that we also internally have constructed a line through those 2 points which plays the role of the line at infinity. Now let me redo the same construction with other points. So let's move my points to that position and redo the construction. So we take our 4 lines here. So these are our original lines of the construction. Then we take the intersection here. You see, now it's no longer in the middle, but it's what we did before. We took this line and intersected them. So I take this line and intersect them. Then we calculated those 2 points of intersection, and we do the same here. So we calculate this point of intersection and this one and join them with the lines. And what we got is a nice, perspectively correct drawing of perspectively distorted rectangle subdivided in 4 equal smaller pieces. I redid this construction with a little bit more dynamics here. So what you see here is the same construction, and I even subdivided the subdivided rectangles once more, and you see how I can produce a nice perspective drawing of a rectangular grid. And if you remember the very beginning of our lectures, then you see that these drawings of the Renaissance painters, they very nicely put rectangular grids on their floors. And this was essentially done by constructions similar to those here, and they are in essence, well, a projective thing. So with that, I want to close this section, and next time we will care about projective incidence theorems and about projective transformations in the real projective plane. See you there.